So once again, welcome to iTelescope, and this is very exciting. It's all about gravitational waves and listening to the universe. So I'm delighted to once again introduce our very special guest, who is in Helsinki, Finland, Dr. Deanna Hooper. Hi, Deanna, how are you?
Hey, Christian, great to be here. Great to come back to the iTelescope network. I really enjoyed giving my first seminar here. It was 2 months ago now. So I'm really keen to give another talk here and to see everyone again. I assume there's going to be some of the same people, and to anybody who didn't see my first one, welcome. Great to meet everyone.
So Deanna, straight to the point, what do you say, what's your comment on the poll?
I love the responses because I'm going to tell you already that most of you got that question wrong. So this is really cool because I'm going to try to convince you, I'm going to show you today just why most of you answered this wrong. And I understand why you did, and that's great. This is awesome because it means that now I get to show you something amazing, hopefully. So I'm really happy to revisit these results halfway through my talk maybe, and then I'll reveal what the actual answer is.
Yeah, and just a quick comment. So put your questions, please, in the Q&A section. So Deanna will stop whenever she wants to or has time, and we'll address that in a bit more systematic manner, but we will definitely address all the questions we can right at the end. So Deanna, without further ado, the floor is yours. Go.
Yeah, let's get started. And just want to say with the questions that last time we had so many that even after 1 hour, I hadn't got through them. So get your questions in quickly because we'll go through the first ones. Okay, so now let me just start sharing. Let's remember to share sound because I have videos today. Okay, perfect. So you should be seeing my slides.
Yes.
Just perfect. Okay, so let's get started. So I want to tell you today about one of my favorite topics, which is the idea of gravitational waves. Gravitational waves are one of the coolest things in the universe. And I hope by the end of this talk, you'll agree with me that they are an absolutely amazing topic. And I just want to mention here, if you like listening to me chat about random stuff about the universe, I have a weekly show called Cup of Cosmology, where I do this pretty much every Sunday. So if you like what you hear today, just Google Cup of Cosmology and you'll find my webpage and the show. And I'm always happy to have more people come onto the show as well. So I'm going to jump straight into the dramatic thing and the reason why we're talking about gravitational waves and the reason why some of you have probably already heard about gravitational waves. And I want to take you back to a day not so many years ago, 6 years ago, 11th of February 2016, when people from the LIGO and VIRGO collaboration called the press conference. And they opened the press conference with, ladies and gentlemen, we have detected gravitational waves. We did it. And this is a historical moment in astronomy. This is a historical moment for anyone who studies the universe. I'm going to show you why today. But what you might have seen after this announcement is every news site, every physicist everywhere was repeating the phrase of a new era for gravitational wave astronomy, a new era for astronomy. We've opened a whole new window into the universe. There was a lot of hype around this. And it's actually become kind of cliche now that every physicist who works on gravitational waves starts their papers with, we are in a new era of astronomy. And every grant proposal we're writing now is, we've opened a new window into astronomy. And there's a lot of hype around gravitational waves. And I hope to convince you today that this hype is completely and absolutely justified because gravitational waves are really, really an amazing topic. So I just wanted to set the scene here with all of the hype around gravitational waves. And now I'm actually going to jump into what are gravitational waves, because that's, of course, the big question now. So to understand what gravitational waves are, I want to take us back to some very basics about general relativity. Now, general relativity is Einstein's theory to explain gravity in the universe. And one key concept in general relativity is that space and time are not disconnected. They are actually intrinsically linked. You cannot have space without time. You cannot have time without space. They are connected together and they form space-time. Another idea with general relativity is that gravity is not just a force in the universe, but gravity is actually the curvature of this space-time. So any object with mass is going to curve space-time. And this has a profound impact on anything traveling through the universe, because anything traveling through the universe will normally travel in a straight line. However, once you're on a curved surface, a straight line no longer appears straight, instead it appears curved. And this is something that we can actually already see here on Earth. We know that the Earth is spherical. I'm not going to entertain any opinions to the contrary. We know that the Earth is spherical. And if you take a plane between, for an example, Barcelona and New York, when you look at the map, just your flat map on the screen, you'd expect, we just fly over the Atlantic and we're done. But if you actually take this plane between Barcelona and New York, you fly up over Greenland. And if you take out your map and you draw the picture, it's a very curved line. And you might wonder, like, why do we go up over Greenland? But actually, because the Earth is spherical, the line between New York and between New York and Barcelona, the shortest path you can draw actually takes you up over Greenland. So the idea here is that any object traveling through the universe will follow the curvature of space-time. So this can be summarized with a very nice concept that objects with mass tell space-time how to curve, and space-time tells objects how to move. And this is like the one-sentence summary of Einstein's general relativity. Now, anytime you move through water, you create waves. Anytime there's a sound wave, it's a pressure wave that's vibrating the atoms in the air. So we're used to the idea that motion in general is going to create waves. And we can actually create waves of space-time itself. So any object that is accelerating through the universe will create ripples in the fabric of space-time. And this is what we call gravitational waves. So gravitational waves are really just ripples in space-time in itself. The thing is, pretty much everything creates gravitational waves. So if I'm here on my spinning chair and I start spinning and flapping my arms around wildly, this is creating gravitational waves because I'm moving, I'm spinning, and there's no symmetry. However, if I were a perfect sphere, physicists like to pretend things are spheres. So if I was a perfect sphere and I rotated at a constant velocity, I would not create gravitational waves. So to produce gravitational waves, you need two things. You either need acceleration or you need a lack of symmetry. So anything, for an example, a rugby ball or an American football ball, if you throw that up, that is producing gravitational waves. So pretty much anything moving through space is going to create gravitational waves. Now, of course, the gravitational waves that I'm creating, flapping my arms around wildly, are ridiculously small and they're not really ones worth talking about, but we are producing these gravitational waves constantly. Now, like any wave, gravitational waves have a few key properties. First, they have an amplitude. So if you're used to making ripples on water, you're used to seeing these waves where they have mountains and valleys, kind of the crest of a wave and a valley. So gravitational waves also have mountains and valleys, and they have an amplitude, which is the distance between the top of the crest and the bottom of a valley. Now, rather than talk about amplitude, what we usually talk about is the strain of gravitational waves. And the strain is just a way of giving the overall impact of a gravitational wave. The larger the strain, the larger the impact the gravitational wave has on an object. Gravitational wave is going to have a frequency, which just tells you how close together the crests and the valleys of the wave are. We have a wavelength, which is the distance between two crests or two valleys. And gravitational waves are going to have a specific speed. And I'll show you later that we actually know that gravitational waves travel at the speed of light, which is pretty cool. But I'll come back to that later. So of course you want to see an example of gravitational waves. So I'm going to show you now a simulation of what gravitational waves look like. So this is not a real event, this is a simulation. And what you can see here in the center of the screen are two black holes. And these black holes are going to orbit around each other and then merge. Just want to point out the grid lines that you see here. Now the grid lines represent space-time. I want to emphasize here that these gravitational waves have been exaggerated, so we don't expect them to be this big. But what you can see here, hopefully you can see the video, you see the two objects orbiting around each other and producing gravitational waves. And they are gradually getting closer and closer and closer until eventually they're going to speed up and they're going to smash together and produce one black hole. You see the waves propagate outwards and now it stops because now we no longer have rotation, we no longer have lack of symmetry, we no longer have an accelerated object. So the two black holes came together, they merged, they produced gravitational waves, and then they stopped producing gravitational waves after the merger had stopped. The next thing we can ask is what impact do gravitational waves have? So now I'm going to play another video, and here we have the idea that every one of these rings represents a ring of particles or a bit of matter or a bit of space-time. And we're going to have a gravitational wave traveling from the back right of the screen to the front left of the screen. So you can imagine it's almost coming out of the screen towards you. This is the direction that the gravitational wave is going to travel. And what you can see here is the effect the gravitational wave is having on your ring of particles. First, it's stretching it in one direction, and then it's stretching it in another. And it looks like this kind of weird, like caterpillar thing that's going to come out of the screen, but this is just the effect of the gravitational waves. It's stretching in one direction, and then it's stretching in the other. So this is the key idea behind gravitational waves. They're ripples in space-time that are going to change distances. They're going to stretch in one direction and then stretch in another. I'm going to take the caterpillar off because it's a bit mesmerizing. So I want to discuss this a bit more specifically, what we're talking about here. So gravitational waves are going to deform space-time, first in one direction and then in a perpendicular direction. So if you imagine you have three axes, three perpendicular lines, you have an up-down direction, you have a left-right direction, and you have an in-out direction. So if the gravitational wave is traveling along the in-out direction, first of all, it's going to stretch on the up-down direction and contract, and then it's going to do it in the other direction. So first we go up and then we go out. If you look at the image on the top right here, this is just a simulation. It's the same thing as what you saw before, but now instead of the cylinder, we're just focusing on one slice of the cylinder. And you can see that first it goes in one direction and then in another. So if a gravitational wave were to go through you, first it would make you taller and thinner, and then it will make you shorter and fatter, assuming it's traveling directly through you. Now these changes in length, this up and down, left and right change, is ridiculously small. So for most of the gravitational waves that we can think about in the universe, the biggest change we can think about is 1/10⁻²1. So this is the strain. This is what I mentioned before, that instead of amplitude, we talk about the strain. And this is how much it's really going to modify the length. So this means it's 1 part in 1,000th billionth billionth. This is a ridiculously small number. So this 10⁻²1 means it's a 1 followed by 21 zeros. So we're saying here that the gravitational wave is going to make you grow by 1 part in 1,000th billionth billionth. Ridiculously small amount. And just to put this in perspective, if this wave is coming through you, as I said before, first it's going to make you taller and thinner, and then it's going to make you shorter and fatter. However, if one of these gravitational waves hits you, it will make you grow by 1/1,000,000th billionth the width of a single hair. So if you take a human hair, you divide it into 1,000,000 billion parts, that is the difference that it's going to make on you. And this is such a small amount, this is such a small thing, which is why gravitational waves are not a good solution if you want to get taller. I'm sorry, they're not going to help you with that, unfortunately. But they will, you just won't notice it. But this is a really, really small effect. So, of course, a big question is, how are we ever going to measure something that is so incredibly small? And I will get to that later. But there is one very important thing about gravitational waves, and that is that they will carry away energy. So gravitational waves, they're not just a ripple in space-time, they're a ripple carrying energy. They carry energy, they carry information. We know that in the universe, energy has to be conserved. It's one of the few things we trust in the universe is the conservation of energy. So this energy has to come from somewhere. And where it actually comes from is this whole process of having two objects. For example, the case of two objects spiraling around each other, this whole process is creating energy. And this energy actually means that this energy being taken away means that these objects gradually get closer and closer. So anytime you have two objects orbiting around each other, they produce gravitational waves and the orbit decays. By a decaying orbit, we mean they gradually get closer and closer until they're going to smash together. And at this point, you might be wondering, we know that the Earth orbits around the sun. We also know that the sun has a slight wobbling motion due to the Earth having the effect on it. Newton's laws, where every action has an equal and opposite reaction. So while the sun is keeping us in orbit, we are having a slight effect on the sun as well. So we have a system here of two objects orbiting around each other. So you could ask the question of, is this system producing gravitational waves? And are these objects getting closer together? And the answer to both of these questions is yes. The Earth is gradually getting closer and closer to the sun due to the gravitational waves that are being emitted. But we don't need to worry about falling into the sun, because over the entire history of the Milky Way, since the sun and the Earth have been here, we have moved about 3 centimeters closer to the sun due to these gravitational waves. The effect is very, very small because the sun is quite small, and especially the Earth is very, very small. And in order to have a really noticeable effect, or something that is at least of the order of this 10 to the minus 21, we need something bigger. And the Earth is just not big enough. But the Earth is producing gravitational waves as it gradually, very, very, very gradually falls into the sun. But, you know, we'll be long gone. The whole of humanity will be long gone before the sun would actually eat us up. So we don't need to worry about that. So this is what you are seeing in the first simulation I showed, where we had the two black holes merging, orbiting around each other and coming together, producing gravitational waves. So this is the key idea here. Gravitational waves are ripples in space-time. And now, of course, we can ask the question of what can produce gravitational waves, apart from me flapping my arms about on the chair. And there are four main categories of objects that can produce gravitational waves. So we divide it into four groups. The first one is the one that I've already shown you, the idea of binary systems. And usually we want compact binary systems. And by compact, we just mean objects with a lot of mass. So this can be, for an example, two neutron stars coming together. Neutron stars are stars made of neutrons. They're a really cool type of star. We'll discuss them more in 2 minutes. So you can have neutron stars coming together. You can have black holes coming together. You can have black holes and neutron stars coming together. All of these binary systems will produce gravitational waves. This is what I showed in the simulation. Something else that could potentially produce gravitational waves are supernovae. So supernovae is what happens when a star reaches the end of its lifetime. The core collapses and it explodes outwards, pushing all of its outer layers out and sends out a lot of material throughout the universe, which can then produce the next generation of stars. Now, a supernova is an explosion, and explosions are usually not symmetrical. If you have any type of deformation of the star, if you have more helium on one side, if you have more iron on one side than the other, you're going to have a lack of symmetry, which means when the supernova explodes, it's going to explode in an unsymmetrical way, in an asymmetrical way, which means that supernovae could actually produce gravitational waves as well. We have not yet measured gravitational waves coming from supernovae, but it's something that we expect could happen. Something else that could produce gravitational waves are pulsars. Now, pulsars are a really curious concept. So I mentioned before that neutron stars are stars that are completely made of neutrons. So they're stars that are so dense that protons and electrons are basically smashed together to form neutrons. So they are some of the densest objects in the universe. And neutron stars are also unlikely to be symmetrical. If you have any type of mountain or valley on a neutron star, because it's actually something physical, you can have things that are not perfectly spherical. So you have a lack of symmetry, but you're still missing some type of motion. And that's where pulsars come in. So pulsars are a specific type of neutron star that is spinning extremely quickly, really quickly. So it's a neutron star that is spinning quickly. If this neutron star has any type of bump on it, this is going to produce gravitational waves. Now, the cool thing about pulsars and why they're called pulsars is due to this really quick spinning, you have a huge magnetic field. So it's a highly magnetized spinning star. And this magnetic field spinning is actually going to create a very high energy jet. It's going to, in the same way that here on Earth, the northern lights are what happens when solar flares get caught in the Earth's magnetic field. If you have a pulsar that is spinning very quickly, it's going to create this huge magnetic field, and it can actually heat up any matter around it and spit it out as high energy jets. So a neutron star usually has two jets, one in each direction. And the thing is, these actually work as pretty much lighthouses. So imagine you have a star that's spinning very quickly and that in one direction has a high focused energy beam. This is basically a lighthouse. Every time it spins around, you get to see the light from the pulsar. This is really cool because we'll see more about pulsars later, but pulsars are basically the lighthouses of the universe, and they might produce gravitational waves. And the fourth thing that could produce gravitational waves is the universe itself. So we know, or we're pretty sure, that in the early universe, the universe was very small, very hot, very dense. And it had this dramatic expansion where every point in space-time moved away from every other point in space-time. The universe grew dramatically. This was such a huge and dramatic effect that we can still see the afterglow of this initial expansion. This is what you can see in the bottom right image here. This is the CMB, the cosmic microwave background radiation, which is the oldest light we can see in the universe in any direction in the night sky. And this is really the afterglow of the Big Bang. but the Big Bang could also produce gravitational waves. So apart from this background light that we see everywhere, there could be background gravitational waves everywhere in the universe that are the leftover from the Big Bang itself. And that's really cool when you think about it, that we could actually still hopefully one day see the gravitational waves that came from the first seconds of the Big Bang. Absolutely amazing. So we've seen what are gravitational waves, what they do, and what can produce them. And I think now is actually, before we jump into a bit of history, now would be a good time to see if there's any urgent questions. Maybe let's see if everything I said so far is clear.
Well, Deanna, very clear so far. We have questions already. So the first question from Thomas, I'm just going to jump that one because you already answered that. We know the speed of light. What is the speed of gravitational waves? So that's that you've answered. I mean,
I'll answer that more later. I'll come back.
I know you. And now comes an exam question for you from Michael.
Ooh.
Here we go. Yeah. For a binary black hole coalescence of two black holes of equal mass, what percentage of the combined mass of the two black holes is given off as energy in gravitational waves?
I can't give you an exact answer because even if you say equal mass, it does depend on the mass of the black holes themselves. But a substantial percentage is actually given off. Let me just calculate in my head. Usually, and this is just a number I'm pulling out here, usually about 5% of the total mass of the two objects is converted into gravitational waves, somewhere between 2 and 5%. So it's a non-negligible amount. You do actually have a substantial amount that is converted into gravitational waves. So if you give me the mass of the black holes, we can do the calculation, but just saying equal mass, then an equal amount of gravitational waves, but obviously not equal to the mass, but a small percentage will be converted into gravitational waves.
Just a curious add-on question to that. You say we can calculate that. I mean, this is nothing that you could do in the sense of using Newton's equation. So you would have to sit down. I mean, even with very simple masses, you would have to sit down on a computer, wouldn't you, Deanna? Or
oh, you would have to use general relativity. I think you could probably do it for one case if you took a while. We could pull this out. But I think actually to calculate the energy, if you remember all of your general relativity, I would need to get a few textbooks, but it's something that we could feasibly calculate. Like, please don't ask me to calculate it, but it would be possible.
Would you like another question, or do you want to go
Let's do one more, and then
okay, one more. Okay, from Edwin. Can anyone travel faster than the speed of light? I have read that after the first minute, the observable universe was about 500 light years across. After a day, 20,000 light years across. After a year, 375,000 light years across. So obviously the universe expands faster than the speed of light. If true, is it possible today to travel faster than the speed of light?
I love this question. This is such a cool question. So it's complicated, but nothing in the universe can travel faster than light in a vacuum. Nothing. You will never be able to travel faster than light. As far as we know, if we figure out faster than light travel, we bin physics and start again. Nothing can travel faster than light. However, you are very correct that the universe itself can expand faster than light in a vacuum. And the reason is that this limit is only really to objects traveling within space-time. It's no such limit on space-time itself. However, I want to mention here that it's, on the one hand, a very sensible thing to ask, but also it's something that we can't really discuss properly, because every time you talk about a velocity or a speed, you have to ask with respect to who. So if I'm moving on a train and I measure another train going by, I'll measure a different velocity than if I'm on a platform not moving. So velocities are always defined with respect to whom. And within space-time, it's easy. It's like, I'm looking at a light beam, I'm looking at this person is looking at that. But how would you define a speed of expansion of the universe? Like, who is making this observation? Because everyone is within inside the universe. So it becomes very difficult to define what we mean by speed of expansion of the universe. In fact, what we usually say is the expansion rate. So how much every patch of universe is growing in a second. But we don't actually usually talk about the speed of the universe because you can't take a frame of reference where you can define such a speed. So the short answer, this is a question that we could spend hours on, but the short answer is there is no reason why the universe should be limited to traveling at the speed of light, but we can't really talk about the speed of the universe anyway. But that is a great question. Okay, so let's get on with the history of gravitational waves. And for the history of gravitational waves, I once again have to go back to general relativity. But before getting to general relativity, already at the end of the 19th century, Heaviside initially proposed the idea that in the same way that we have electromagnetic waves, maybe we could have gravitational waves. But he didn't use the word gravitational wave. He just was thinking, like, could we have ripples of gravity? And then Poincaré in 1905 was actually the first one to use the term gravitational waves. And he proposed the idea that in the same way that any electric charge that is accelerating produces an electromagnetic wave, any massive object that is accelerating should produce a gravitational wave. So Poincaré was the first one to actually kind of think about the concept of gravitational waves. Then 10 years later, Einstein publishes his general theory of relativity, 1950. The thing is that gravitational waves are a numerical solution to Einstein's equations. If you solve Einstein's equations of general relativity, you pull out gravitational waves. And you can actually pull out 3 types of gravitational waves. And these are called longitudinal, longitudinal, longitudinal transversal, and transverse, transverse. And this is just talking about the direction along which the waves are propagating. And immediately after Einstein put out his general relativity, it was shown that the longitudinal, longitudinal, and the longitudinal transversal gravitational waves were just mathematical artifacts that had no meaning. So they were discarded as possible solutions. And that left the third type, the transverse, transverse. These don't worry if you don't know what I mean by transverse, transverse. It's just a name we give the waves, which is just related to in which direction they vibrate. But Einstein was a bit skeptical and also said this third type is probably just a numerical artifact. This led to a lot of discussion, and it was actually shown that it was not a numerical artifact, but it was a valid solution to the equations. And not only a valid solution to the equations, but a key prediction. So if Einstein's general relativity was correct, you should see gravitational waves. At some point, about 20 years after Einstein initially proposed general relativity, people began to accept the idea, like you cannot have general relativity without gravitational waves. It's not just a numerical artifact, it is something we need in our equations. Then in 1957, Feynman, who you might have heard of, he's considered by many to be one of the fathers of particle physics. He did the Feynman diagrams. He's a very well-known physicist. I'm not going to get into the potential problematic parts of him because we could do that with every physicist. But in 1957, Feynman showed that these gravitational waves had to carry energy. He concocted a thought experiment, which was the moving beads, with the idea that if a gravitational wave hits a rod with beads on it, these are going to move slightly. This will create friction, and this friction will create heat. And if you are heating something up, it means you've done some amount of work. And if you've done any amount of work, it means there's energy in the system. So with this thought experiment, Feynman was able to show that gravitational waves not only exist, or should exist if general relativity is correct, but they should carry energy. So by the 1950s, 1957, people accepted that gravitational waves should be a thing. Then in the 1960s, Weber started working on the first concept of a gravitational wave detector. The idea here is Weber had a very big metal rod. I think it was made of tritium. I'm not completely sure, but you have this big metal rod, and he was hoping to see any type of changes in the distance. In fact, in 1969, Weber claimed that he had detected gravitational waves. And at some point, he was claiming to be detecting gravitational waves on a regular basis. However, no other team was able to verify this. And at some point, they realized that he was just basically picking up noise and that his detector wasn't actually working. So there wasn't a detection, but this was one of the first ideas to try to measure gravitational waves. Then the story of gravitational waves became much more interesting and much more tangible in the 1970s. So in 1970, Hulse and Taylor found a pulsar. If you remember from before, a pulsar is this rapidly rotating neutron star that I described as the lighthouse of the universe. So Hulse and Taylor found a pulsar that is rotating 17 times per second. I mentioned before that these move quickly, and now I'm actually giving the number. 17 times a second, this lighthouse spins around. So very, very fast. If you consider this is something that is about 1.5 times the mass of our sun, and it is whipping around so quickly that every 17 times in 1 second, you get to see this light beam. Really fast. And I just want to mention that they actually detected this using the Arecibo Observatory, which was an observatory in Puerto Rico, which a lot of people felt it was a very nice observatory. And unfortunately, it had a very dramatic and nasty crash at the end of 2020. And of course, 2020, because that was the year. And it's no longer operational, unfortunately. It basically crashed, and it was a very sad day for astronomy when we lost the Arecibo Observatory. But in any case, Taylor found the pulsar. But apart from the fact that it was rotating 17 times a second, there was another curious thing. And that was that there was a very slight change in the time of this pulse. So sometimes it was slightly earlier, and sometimes it was very slightly later. And what this showed is that the pulsar was actually locked in a binary system. So you had one object that was emitting this lighthouse-style beam of light, and another one orbiting together. And it was actually shown that the other object was also a neutron star. So we had two neutron stars orbiting around each other. So we're starting to have what we need for gravitational waves. Two neutron stars orbiting around each other, and one of them is spinning and producing this light beam. They were orbiting around each other with a period of 8 hours. Now, Taylor made several observations of this pulsar over the years. And what they actually found is that this period of 8 hours was gradually decreasing, which meant the orbit was gradually decaying. So in fact, these two objects were gradually getting closer and closer and closer. I'm going to show you now the diagram of what this looked like. So on the horizontal axis, you just see the year of the observation. Every red dot here is an observation. And on the vertical axis, you can just see the overall difference from the initial period in seconds. And you can see it's a very small shift. We're talking about 5 seconds over the span of 10 years. But this was detectable. So every red dot here corresponds to an observation. And the blue line you can see in the background is the prediction of Einstein's general relativity of how the orbits would decay if they were emitting gravitational waves. And you can see that the observations and the predictions are in very good agreement. So this was considered the first indirect measurement of gravitational waves, because we didn't see the gravitational waves themselves, but we saw the after effect of these two neutron stars gradually getting closer and closer, losing energy that had to have been carried away by gravitational waves. Indirect proof of gravitational waves. Taylor were awarded the Nobel Prize in Physics in 1993 for the discovery of a new type of pulsar, so the pulsar in a binary system, and its impact on general relativity and how we could study it. Because now we have an observation. We don't have direct gravitational waves, but we did have something. Of course, measuring things indirectly is fun, but what we want to do is measure gravitational waves properly. We actually want to see not only the after effect, we want to see gravitational waves. But I mentioned before that this is such a small effect. How do we go about measuring it? We also have the other problem that if you construct a ruler and you try to measure distances and a gravitational wave travels through you, it's just going to stretch your ruler. So how can you possibly measure gravitational waves? And I think the answer to this question is an incredible feat of human ingenuity. And the answer is we use light. So to understand how we use light to measure gravitational waves, we need to go back to two key concepts. The first one is going back to Einstein's general relativity. The speed of light in a vacuum is always, always, always constant. Light will always travel at the speed of light. And this is something that is a bit counterintuitive. I used the example before of being on a train. So if I'm on a train traveling at 50 kilometers per hour, and another train passes by traveling at 100 kilometers per hour, I will measure their speed as being 50 because I already have my own speed, whereas someone on the platform will measure their speed differently. So depending on your own motion, you measure a different speed. This does not happen with light. If I'm traveling, if I hypothetically could travel at the speed of light and I turn on a torch, that light is still going to travel away from me at the same speed of light. Regardless of who makes the observation, regardless of the speed of the observer, light will always travel at the speed of light. This is Einstein's general relativity. You cannot get around this. You can't say, I'm going to travel at the speed of light and catch up with the light beam. The light beam will still travel away from you at the speed of light. It sounds counterintuitive, but it is the way it works, and we've been able to prove that this does happen. Now, when we're talking about the speed of light, as we know, any speed is just the distance over time. So if we're saying here that the speed has to remain constant, now imagine I have this fraction here, speed is equal to distance over time. If the speed, the left-hand side is always the same, if I change the distance, the time has to change. If I change the time, the distance has to change. This means that if you increase the distance between two objects, the time it's going to take light to travel is going to be longer. If you decrease the distance, light will travel there faster. Not faster, sorry, but quicker. So you can use speed of light as a ruler. We know that the speed of light is always constant. If we know how long it took light to travel a specific amount, a specific distance, you can know that distance because we can use light as a ruler. So this is the first idea that we need to remember here, is that the speed of light in a vacuum is always constant. The second key thing about light is that light is a wave. Because light is a wave, it's going to have mountains and valleys, or crests and valleys, the same as before. If two waves meet, they are going to interfere with each other. They're going to have an effect. And you can see this if you go into a swimming pool and start making ripples. If you make ripples with one hand, they'll move out from your hand. If you make ripples with the other, they'll get an interference pattern where the light beams come to, the water waves come together. So what you're going to see in this simulation here in the middle, or this sketch, is two waves, one traveling left to right, which is going to be a blue one, and one traveling right to left, which is going to be a green one. And the red one is going to show us the sum of the green and the blue, so the overall effect. So you see here you have blue, sorry, going right to left, green going left to right, and when they come together, you have the red one. So when two mountains meet, you have a taller mountain. When two valleys meet, you have a deep valley. But when a mountain and a valley meet, they cancel out. So this is what is known as constructive interference, if it's two mountains or two valleys, and destructive interference, because you're destroying the wave if it's a mountain and a valley. So light acts as a wave and it moves at constant speed. And with these two concepts, we can build a gravitational wave detector. We just need to know that light always travels at the speed of light and that waves are going to create interference. And with this, we can create what we call an interferometer. So I'm going to show you a video of how this works, and I'm going to explain the video as it goes. So we start by producing a laser light beam. This laser is going to be split along two paths. It's going to be sent down the arms of your detector, where there's mirrors, and this is going to allow us to detect them. Let's go through it slowly. We produce a light wave, which has a wave. We split it into two parts. It travels down the arm of a detector until it finds a very, very polished mirror. It comes back. Now, when it comes back, these two light beams are recombined, they're put together. If there is the distance in both arms is the same, they come back in perfect phase. They do not interfere with each other. They destruct, and you don't get anything. However, if something changes one of these lengths during this passage, you're going to have constructive interference, and your detector will actually get a signal. So, going through this again, you send the light beam down to a light splitter. It splits the laser beam in two. It sends these lasers down different paths that are exactly the same length. This comes back together and you put the light beam back together. At this point, you have destructive interference. No light beam is detected. If one of these two lengths changes by a small amount, by the time light comes back, it will not be in perfect phase anymore. The waves will interfere with each other with constructive interference, and they will create a signal that you can measure down here on your detector. And I just want to let that sink in for a minute here, because what we're saying is we're using lasers to try to detect gravitational waves. Now, in order to do this properly, you don't just send the laser down once in each arm, you send it down thousands of times in each arm, because then you increase the sensitivity to tiny, tiny, tiny distances. And this might seem like a sci-fi, fantastical, far-fetched concept, and it is, but it's also a reality. This is exactly what we did. This is exactly what has been built. So the first two gravitational wave detectors of this type were LIGO Hanford and LIGO Livingston in the US, separated by 3,000 kilometers, one in Arizona, one in Washington. You can see them both here, and they're basically just tunnels with the machine at the center and these very two long arms. I think the Livingston one looks prettier, it has trees around it, the other one is in a desert. There is now one in Italy as well, known as VIRGO, in the north of Italy. There was also one in Japan, known as Kagra, but that only turned on very recently. There was one planned in India, and there was also one planned that's in the wrong color in this figure on the bottom right, but there was another one planned in the center of Europe. And all of these use this idea of we take a beam of light, we throw it into, and we try to use this beam of light to find gravitational waves. So LIGO stands for the Laser Interferometer Gravitational Wave Observatory. As I just said, there are two of them, one in Livingston, one in Hanford. Each one of them has two arms. The arms are 4 kilometers long, which is 2.5 miles. And the thing is, apart from the laser and the arms, the hardest part of building a gravitational wave detector is the signal you're looking for is so small that anything can get in the way. If you have a truck passing by your detector, you will get a signal. If you have a train passing 100 kilometers away, you will get a signal. So you need to have a completely isolated detector. And what they do is the mirrors are actually suspended in a way that any local vibration can be accounted for. So you have perfectly suspended, isolated mirrors that are absolutely polished with no imperfections, because any imperfection in the mirror could result in a signal. So ridiculously difficult engineering feat. But LIGO and VIRGO were able to do it. Now, LIGO initially ran from 2002 to 2010, and it did not detect anything. So they switched the machine off, they upgraded it, they made it 10 times more sensitive, they renamed it Advanced LIGO, and they turned it on again in 2015. VIRGO, the one in Italy, initially ran between 2007 and 2010. It also did not detect anything. It was shut down, rebuilt, they made it 10 times more sensitive, and Advanced LIGO turned on in 2017. And now LIGO and VIRGO work together. And the reason they work together is because if you have three objects making a detection or trying to make a detection, you can triangulate the source of the signal. So here we are. We have our detectors. We have the concept of a laser interferometer. We have LIGO, we have VIRGO. And I want to take you back to August 2015. September 2015, sorry. September 2015. Specifically the 14th of September 2015. Because this is the first time that the LIGO detector measured a gravitational wave. This is the event that led to the press conference of, ladies and gentlemen, we have measured gravitational waves, we did it. We measured gravitational waves for the first time on the 15th or 14th, I think I might have just mixed up the numbers. Anyway, you can see it in the top right corner, you can see the date there. It's covered by my Zoom window. So September 2015, LIGO went off with the first detection of gravitational waves. So what you can see here is four different panels on the left and 4 on the right. The left is Hanford, the right is Livingston. The very top panel is the actual signal that they picked up. The second panel is what we would predict from general relativity, a prediction from general relativity of what a gravitational wave might look like. The third panel is what happens if you subtract the first two. So you subtract the prediction from the signal, and you're left with something that is practically zero. This tells you how closely the signal matches the prediction. And what you can see at the bottom, time goes from left to right in all of these panels. In the bottom panel, you can see the frequency going up, and in the colors, you can see the strain of the gravitational wave. So LIGO shut down in 2010 after not detecting anything. It turned on again in 2015. And within 10 days of turning on as Advanced LIGO, they got a signal. And it was so close to the machine turning on again that the people involved actually thought it was a test signal. One thing that LIGO does is what they call a blinding and an unblinding that a lot of experiments do. So this signal went off in the detector, and everyone gets to work, assumes it's a signal, and does all the calculation of, look, this is what we found. It's a test one, or it might not be. They go through the whole work, and then they ask the other people, like, did you put a test into the machine, or is this a real signal? This is the unblinding part, where the other team say, yes, it's a fake signal, or no, it's not a fake signal. So the team got this. It was 10 days after they turned on, and they was like, okay, this is another test. They did the full calculation, then they did the unblinding, and it was not a test signal. This was actually the first detection of a gravitational wave. It was announced in February 2016, but it was detected in September 2015. the first ever direct detection of gravitational wave. And now I want to pause. And you'll see that the title of this slide is Listening to the Universe. In fact, the title of my talk today is Listening to the Universe. And now I want to explain why. Because these gravitational waves have a frequency. Every wave has a frequency. And the cool thing is there are some waves that we can hear, sound waves we can hear. Now, these are not sound waves, these are gravitational waves. However, the frequency just happens to match the frequency that is within human hearing. So these are not waves that we can directly hear. I want to make this clear. We do not hear the gravitational waves, but we can pretend that it's a sound wave. We can convert it to a sound wave. So we can ask the question of what would a sound wave of the same frequency sound like? The same frequency and the same amplitude. So we can turn this gravitational wave into a sound. We can actually listen to the sound of gravitational waves. I make this claim, and of course we have to listen to this. So I'm going to play this clip now. I'm going to play to you the sound of gravitational waves coming from two black holes smashing together. And this was the first detection. We're going to hear the sound a few times. Now, first you'll hear a slightly deeper one, which is the exact frequency of the detected gravitational wave. And then we'll hear a slightly higher version, which is just shifted into a range that is better for human hearing. So are you ready to hear the first ever gravitational wave? I'm not going to wait for answers, let's just go. So you're going to hear first the real frequency and then the adjusted frequency. Let's go again. So you just heard the chirp of the first ever gravitational wave measured by humans. And this is amazing. And this is what almost half of the scientists I know had this as their ringtone for a while, because we just listened to the sound of two black holes smashing together. Two black holes smashed together somewhere in the universe. They sent ripples throughout space-time. We picked this up here on Earth using lasers sent down a detector, and we turned it into a sound wave so that we could listen to the universe. For the first time, we have not just seen the universe with our eyes, we just listened to the universe. Phew, that never, ever ceases to amaze me. So the good thing is, we've been ready for this. We knew that this signal was coming. And since the late 1990s, we've actually had the computing power to run hundreds of simulations of what might a gravitational wave look like? What might we measure one day? And we've simulated thousands of different possibilities of black holes smashing together, of neutron stars smashing together, black holes and neutron stars smashing together. And now what happens is when we get a measurement like this one in 2015, we compare it to our existing catalog of templates. We run through the templates. If I go back here, you can see in the second panel, there's a template here. And it says in the legend, the numerical relativity. So this is one template. So when we get the signal, what we do is we go back, we take our catalog and we match which of our catalog, which of our studied examples best fits. You might find 2 or 3 that are closest, and then you take the average of them, you put them together. So we've been ready for this. We've been ready for this signal. So this one that was measured here on the 14th of September in 2015, which is known as GW150914, which is just gravitational wave in the date. We know from comparing to our existing templates that 1.5 billion light years away, which means 1.4 billion years ago in the history of the universe, 2 black holes, one of 36 times the mass of the sun, one of 29 times the mass of the sun, started a cosmic dance. They started spiraling around and around and around each other, getting closer and closer and closer. And they eventually smashed together, creating ripples throughout space-time. And these ripples carried away 3 solar masses of energy. So what you can see here are the numbers. One of the black holes was 36 solar masses, one was 29 solar masses. The resulting black hole that was left at the end was 62. And if you do some basic math, you'll see that 3 solar masses are missing. Those 3 solar masses, 3 times the mass of the sun, was converted into energy, was converted into gravitational waves that traveled 1.4 billion light years in the universe, and then hit our detectors. They hit our lasers, and we were able to detect them. So this was the first gravitational wave measurements, but the journey did not end there. This was 2016. LIGO, VIRGO have been working hard since then. And now we are at the stage where we have measured 90 gravitational wave signals. And this goes back to the question we had at the beginning, where most of you thought it was 10, 20, 30. We have measured 90 gravitational waves. LIGO, VIRGO have been triggered 90 times. And in the early days, I was getting Twitter notifications, and every time it happens, like, oh, here's another one. And now it's so commonplace that it's like, oh yeah, we've done it again. But it is amazing. So what you can see here is the catalog of everything detected by LIGO and VIRGO. And I should mention that this is only after run 2 in a minute. So here there's only 60. In a minute, I'll show you run 3 with the remaining ones. So what you can see here on the vertical axis is the mass. So the lower down it is, the smaller the object, and the higher up, the more massive. And you can see that it's always 2 objects that are joined by a line that goes to a third one. So this is 2 black holes in blue, for an example, that join together and create a new one. And you can see that here we have the black holes shown in blue, and we have the neutron stars shown in yellow or orange. So the ones here referred to as EM means we found them with other means that is not LIGO and VIRGO, without gravitational waves. But you can see here that there are a lot of these that are black hole going together. And if you look down at the bottom of the screen, there are some special ones, which I'll come to in a minute. But let's look at the full catalogue after 3 observing runs. This is the complete picture, everything that LIGO, VIRGO have measured. So now you'll see here in the legend, there's also Kagura, because this is the Japanese one that has turned on. The first run in the lightest blue top left gave us 3. The second run gave us another 8, sorry. The third run gave us 60. The second part of the third run gave us another 30. We are now in total, I know I did the math wrong there, but in total, 90 observations. And I love this image because there's a lot of surprise faces. So the top 2 corners, left and right, show you the original black holes, and the middle part is the final black hole. 90 observations. This is commonplace now. I know a lot of you thought it was 10, it was 5, it was 20, and it's a reasonable guess because this is absolutely amazing. We have black holes smashing together somewhere in the universe, and somehow we are measuring it here on Earth using lasers. And we've done this 90 times. I don't yet believe it. I understand why 2 people voted on 90 because it's amazing. But I want to focus on the most amazing observation of all, which is this one here. And you'll notice that instead of 2 black dots in the top right corner, we have 2 light blue dots. So this was the first time that LIGO and VIRGO measured 2 neutron stars coming together and merging. And the reason this is so important is because when 2 neutron stars smash together, not only do they produce gravitational waves, they also produce electromagnetic waves. So we get the gravitational waves coming from the objects spiraling and smashing together. And then this results in a kilonova, which is like a supernova, but not as powerful. It's an explosion that is visible. So this means we can do something known as multi-messenger astronomy. We can look for this gravitational wave, and we can look for the electromagnetic part as well. So in 2017, what happened is these 2 neutron stars got close together, smashed together, and produced gravitational waves. This was measured here on Earth on the 17th of August, 2017. And the LIGO VIRGO detectors found this gravitational wave signal and alerted the team like, hey, gravitational wave. Within 2 minutes of the signal arriving at the detector, the astronomers had been notified. On the other hand, people were working on gamma ray experiments such as Fermi, which measures high energy beams of light. And they measured something coming from the same direction of the sky. They measured a huge gamma ray burst. And they sent out the signal within 40 seconds. So 2 minutes, like within 5 minutes of these events being measured, both in gamma ray and gravitational wave, the entire astronomical community working on telescopes got a notification of, hey, we might have just seen something. And at this point, if you have 2 neutron stars smashing together, you get 3 things. You get the gravitational waves, you get the initial gamma ray burst from the initial explosion, but you also get the material that is pushed out from the neutron star. You get a cloud of basically neutron poop, which is highly dense elements. And this glows and gradually fades. And this glow lasts a couple of days, which means now a lot of astronomers across the world got a notification of, hey, point your telescopes up there and tell me if you see some glowing matter in the universe, because it might just be the afterglow of a kilonova. 70 telescopes across 7 countries pointed up and found this. They found this glowing neutron star residue, the residue of 2 neutron stars smashing together. We measured it with gravitational waves. We measured it with gamma ray burst. We measured it with 70 other telescopes all the way across the electromagnetic spectrum. We traced it for 3 whole days as it gradually got dimmer and dimmer and dimmer. And this is absolutely amazing. This is the definition of multi-messenger astronomy, an event that produces so many messengers that you can look at it in many different ways. And I want to show you a simulation of what this looked like. On the left, you're going to see the 2 stars themselves, and on the right, you see the gravitational waves. You can see it here. They smash together and produce a huge amount of gravitational waves. So I just want to give you some numbers here. So what we're talking about here is 2 neutron stars, both of around 2 times the mass of the sun, about, let me get that number correct, 130 million light years away. 2 neutron stars smashed together. They produced a kilonova, a huge explosion of light. They were detected in gamma rays and in gravitational waves and in every other telescope across the electromagnetic spectrum. And this was absolutely amazing. And the paper announcing this has 4,000 authors. This was a community effort. So many astronomers in the world looked at this. It also means that this was probably one of the worst kept secrets in astronomy, because technically everyone is sworn to silence until the paper is released. We all knew, we all were ready for this, because astronomers did not keep this quiet. We were all buzzing, but most of us kept quiet. There were a few people who tried to spread rumors on Twitter, but we knew this was coming. And when it was announced, it was so exciting. So we have done this 90 times. We have found 1 case of neutron stars smashing together. So what have we learned so far? What do we know? Well, there's a lot we have learned. One of the biggest things just from this neutron star event is that gravitational waves travel at the speed of light. And this is a prediction of Einstein's general relativity. If general relativity is correct, gravitational waves should travel at the speed of light, because it is the speed at which the universe talks to itself. It's the maximum speed of information. There are people who work on theories beyond Einstein, and maybe Einstein was wrong and we should change this. But the moment we confirm that, based on the time it took the gravitational wave signal to arrive and the gamma ray burst to arrive, they basically arrive within 1.5 seconds of each other, which is completely what you'd expect if they travel at the same speed. So we were able to confirm that gravitational waves travel at the speed of light, and Einstein's general relativity was once again correct. We now have 90 events. This means that we know for sure that black holes exist. We've measured black holes. We now have over 170 black holes within the LIGO catalog. We also know there's a lot of them. We have now got direct evidence of black holes, and we have found over 100 of them. We've also learned that 2 neutron stars smashing together produce gold. They produce platinum and lead. In fact, this event where the 2 neutron stars came together produced 3 times the mass of the Earth of gold. We can't mine it, it's useless to us, but we know that this is where gold comes from. This is where platinum comes from. If you have a gold ring, it's quite likely that that gold came from 2 neutron stars smashing together somewhere in the universe. We also now know that neutron stars smashing together produce gamma ray bursts. We didn't know where gamma ray bursts came from before, now we do. And very interestingly for me personally, we got an independent measurement of how quickly the universe expands, which is good because there's an ongoing debate about how fast the universe expands. We get different measurements depending how we do it. Gravitational waves is a whole new way of measuring this. It didn't help us answer the question, but it will in the future. And all of this is amazing. It's incredible, but this is only a small part of the story. And I want to show you the other part of the story now, because everything I've talked about today is a small piece. So in the same way that electromagnetic waves have a frequency, they have a spectrum. You can go from low energy microwave to high energy gamma ray bursts. You can do the same with gravitational waves. So there's a lot of stuff here, but first of all, I want to focus on the middle band, the standard rainbow that you're used to. You'll see that this just shows you the different frequency. On the left, you have very low frequency, low energy. On the right, you have high frequency, high energy. This is what we're used to with the electromagnetic spectrum. But now let's talk about this in the terms of gravitational waves. And I want to just go to the top. Now, first of all, you'll see there's these quantum fluctuations of the early universe. These are the gravitational waves that could be produced by the Big Bang itself. And you can see that these span the full frequency range. Next, we have supermassive black holes smashing together. This is something that would be medium energetic. This is something that could also be produced. These are different things, different ways of producing gravitational waves. Then in blue, you can see we list here the compact binaries. These are neutron stars and black holes smashing together. These are the ones we've detected. And then we have rotating neutron stars on the right. These are the ones we're hoping to detect, haven't yet found them. And then there's this nice part in the middle here of compact objects captured by supermassive black holes. This is the case of a normal black hole falling into a supermassive black hole, or a neutron star falling into a supermassive black hole. This will produce a huge amount of gravitational waves. And now let's go to the bottom of how we could detect these different things. On the rightmost part, you can see LIGO VIRGO, and you see that it only covers a very small part of the gravitational wave spectrum. If we go to the far left, you can see the CMB, the cosmic microwave background radiation, which could itself have an imprint of these early universe gravitational waves. Then there's something called pulsar timing, which is using these spinning lighthouses in the universe, and any difference in their timing could potentially tell you about gravitational waves. But there's another way we can measure gravitational waves. And you can see that this part that is colored here covers all the possible types, almost all the possible types of gravitational waves we could detect. And this is a gravitational wave detector in space. So taking all of this awesomeness and shooting it out to space. And why do we want to do this? What could we hope to detect? So I mentioned before that the Big Bang itself could produce gravitational waves. But this is not the only thing that could produce what we call early universe gravitational waves. If at any point in the history of the universe there's a dramatic change, like forces breaking apart, which we know happens, it could produce gravitational waves. There could be a background of gravitational waves everywhere in the universe. And these would be a treasure trove of information about the first half of a second, or the first picosecond, the first fraction of a second of the universe. Can you imagine if we were able to point a detector somewhere in the sky and say, look, here is the residue of something that happened 13.82 billion years ago. Here is the first second of the history of the universe. It would help us understand our place in the universe, where we came from and where we're going. But these are much smaller than normal gravitational waves. We need to go to space. A gravitational wave detector on Earth will never be able to do this, but one in space would be. And this is not just a sci-fi concept. This is a planned space mission. So here comes LISA, the Laser Interferometer Space Antenna. It is an ESA mission, European Space Agency mission, that is planned. It has been fully funded, and the construction is ongoing. It is going to be a space-based mission. And the idea is we're going to have 3 satellites that are going to be kept in a perfect equilateral triangle, and they're going to be chasing the Earth. So they're not going to be orbiting around the Earth. They're going to be following the Earth around the sun. They're going to be separated by 2.5 million kilometers, which is 1.5 million miles. So we have 3 satellites in a perfect triangle with 2.5 million kilometers between them, with lasers going back and forth, measuring tiny, tiny, tiny ripples in space-time with incredible precision. Now, the idea of LISA, you have the 3 spacecraft, so you basically have 6 of the LIGO VIRGO interferometers, because each spacecraft can send lasers to 2 others. So spacecraft 1 is going to send lasers to 2 and 3, 2 will send to 3 and 1, and 3 will send to 1 and 2. You can send it in both directions, so you basically get 6 arms instead of the 2 that you have here on Earth. This is scheduled to launch in the late 2030s. Current date is about 2037. This means that 15 years from now, we will be launching a mission that's going to go to space. It's going to be chasing the Earth, and it is hoping to measure the ripples in space-time coming from supermassive black holes smashing together, coming from small black holes falling into big black holes, coming from the universe itself, and coming from who knows what else. Who knows what else we're going to measure when we send this to space. This is going to happen within my lifetime. And that is Incredible. So I just want to show you one last simulation, which is a simulation of what the LIGO spacecraft is going to do. And this is a simulation made by a PhD student in the group in Helsinki. Her name is Anna Kormo. She made this simulation. She has a YouTube channel called Cosmo Blend if you want more. So what you can see here is the sun at the center, the Earth moving around the sun, and these 3 satellites shooting lasers in between them, chasing around the Earth. And here you can see an exaggerated gravitational wave. And this is going to launch very soon, 15 years from now. Incredible. So let me wrap up because I've been chatting for an hour now. So let me wrap up. Gravitational waves are ripples in space-time. They are a prediction from general relativity, and we have now been able to observe them. We are the first generation of humans ever to be able to say we have measured gravitational waves. And we haven't just done this once. We have done it 90 times. For each one of these, we can get a sound wave. We can get the chirp of the universe. Up until now, up until 6 years ago, we'd only been able to see the universe. And now we've turned on the sound. We've turned up the volume. We are the first generation of humans ever to listen to the universe. We have already learned a lot from them. We've learned so much. But the story is just beginning. We are at the infancy of a whole new field of astronomy. There is so much more to do and so much more we're going to learn within our lifetimes. So if there's one thing I hope you take away from this, apart from my enthusiasm for gravitational waves, it is really a new era for astronomy. The hype is justified. It became cliche, but it is true. We are ready to listen to the universe, and I, for one, cannot wait to see what it's going to tell us. So let me thank you all for listening to me ramble for 1 hour about gravitational waves.